All right, hello, greetings. Let's take a look at this is problem 1 from chapter 10. Your company faxed you some results shown below for the system hydrogen methane. Use the data to answer the following. So let's just take it one at a time. So A, because the fax machine malfunctioned, some entries were missing. Supply the missing numbers and explain your calculations. All right, cool. So in the table below, all right, so we've got data for hydrogen and methane, hydrogen component 1, pressure, temperature, we've got mole fractions, so that should be liquid and vapor. Then we've got fugacity coefficients, so subscript would be the component, and the superscript would indicate the phase, so liquid or vapor. And then here it looks like we have compressibility of the phase. So let's take it one at a time. All right, so what's missing, all right, yeah, so what's missing is first we're going to need V1 of my liquid, right, in the second column. Okay, so V1 liquid's missing, and then also here V2 vapor for the second column. So how am I going to calculate it? All right, so first, if I look at the data, in the first column, all right, x1 is 0, y1 is equal to 0. So this is going to correspond to a system of pure component 2. When I look at this system, right, I have an x1 value and then a y1 value, which are different, right? But what this indicates to me is since I have some component 1 in a liquid and vapor phase, right, that this must correspond to this binary system at two-phase equilibria. Right, I must have this binary system at two-phase equilibria for me to have some mole frac of component 1 in both my liquid and vapor. Okay, cool. And so if I have a binary system at two-phase equilibrium, how am I going to get the fugacity coefficient of the liquid? Well, I know at equilibrium, the temperature of the two phases is the same, the pressure is the same, right? But we're given just one T and P, and then the fugacity of each component in each phase is the same. So if I start with component 1, right, I know that the fugacity of component 1 in the liquid phase is going to be equal to the fugacity of component 1 in the vapor. And now if I expand it out, so the fugacity of component 1 in the liquid, okay, that's going to be equal to x1 times V1L times P is equal to vapor y1 times V1V times P, right? And so we have fugacity coefficient times, right, y1 times P and x1 times P. Well, that's the fugacity of an ideal gas. That's just partial pressure. Okay, so the pressures cancel, so I cancel P, and I'm left with, so I'm going for V1L. V1L is going to be equal to y1 over x1 times V1V. Okay, cool. So I know y1, I know x1, V1V, I know V1V, so I'm going to get V1L, right? Great, right? And so since y1 is greater than x1, this will be greater than 1, so V1L is going to be greater than V1V. So I have MATLAB over here, and so I'm going to go and calculate it. Okay, so this is set up for problem 1. Okay, so y1 was equal to 0.9876. Okay, x1 was equal to 0.2. And then V1V, so V1V was equal to 0.9479. Cool. Let's add a comment. This is part A. So computing then, V1L is going to be equal to y1 divided by x1 times V1V. Okay, times V1, because I call it, fill. Oh, no, never mind. It's V1V. It's not going to call it fill. It's V1V, V1L. All right, so it's just in the font, the ones and L's look super similar. So I take that back. So running, all right, I get V1L is 4.6807. Okay, so V1L, okay, which is this number here is going to be equal to 4.6807. Okay, cool. Right, and so I find that the fugacity coefficient of my liquid's greater than that of my vapor. Okay, seems reasonable. Okay, remember, phi of an ideal gas, right, is going to be equal to 1. Right, so the phi of my liquid phase is much greater than the phi of my vapor phase. Okay, so continuing with A, so there's phi1L. Now we need phi2V. Okay, we're going to do the same thing. So I'm looking along this bottom row, which I'm going to have a two-phase system at coexistence. And so if I do the same thing, so I know that phi1, or phi2, I got to write my phi2 liquid is equal to F2 liquid is equal to F2 vapor. Okay, so expanding, X2 times phi2L times P is equal to Y2 times phi2V times P. My pressures cancel, and so I'm going to end up with phi2V is equal to X2 divided by Y2 times phi2L. Okay, and just for completeness, X2, that's 1 minus X1, Y2, 1 minus Y1 times phi2L. Okay, so phi2V is equal to, okay, let's come over here. So I need phi2L. Phi2L is 0.0126. Okay, so phi2 vapor was equal to, and actually I'm going to define, let me just define Y2 as being equal to 1 minus Y1, and X2 is 1 minus X1. So it makes sense. So I have X2 divided by Y2 times phi2L. Okay, so solving phi2V is going to be 0.8129, right? And again, my liquid phase value, right, is really, really small, right? So it's close. And then my vapor phase value is closer to 1. Okay, cool. So this is going to be 0.8129. Okay, cool. All right. So I'm going to turn my camera off since it just froze, right? And we will, nope, turn it on doesn't do anything, so let's just keep going. Okay, so then if I look at what's next, so there's A, I filled in the rest of the table. Then B, it says, what is the saturation pressure of methane at 250 Kelvin? Okay, well, so methane is component 2. So if I look at my first row, okay, this would correspond to pure methane since X1 equals Y1 equals 0. Okay, now the question though is, I want the saturation pressure. Okay, so the question is well, okay, this is pure methane, but is it pure methane at two-phase coexistence? So how I could check is we have the fugacity coefficients of component 2 methane, of my liquid and vapor, right? And I see that they're the same, right? And so since I have a pure component system, right? And so if I were to go back to one of these simplified equations or one of these expanded equations for a mixture, with my pure component system, the mole fractions are the same, right? So those would both be equal to 1. So my iso-fugacity equation would reduce to an iso-fugacity coefficient criteria. So knowing that, when I look at my first row, not only is it pure methane, but it's pure methane at vapor-liquid coexistence. Okay, cool. So then if I want the saturation pressure of methane, it must be this. Okay, so for B, it must be then the P2 sat, the saturation pressure of methane at 250 Kelvin, so at 250 Kelvin, that's equal to 0.074 bars. Okay, cool. So that's B. Now C, calculate the fugacity of saturated liquid methane at 250 Kelvin. right, to calculate the fugacity of saturated liquid methane at 250 Kelvin. So how I'm going to interpret that is if I look at my first row, so I have methane at vapor-liquid equilibrium. And so what I want is the fugacity of my saturated liquid, so my liquid phase. Okay, so I can get that a number of ways. But for C, right, the easiest way is going to be, so I'll call it F2 sat, okay, at, temperature of 250 Kelvin. Okay, so I could calculate that as V2 vapor times P, which is equal to V2 liquid times P, right? And oftentimes these V's, right, I could just call a V2 sat. Okay, talking about a pure component system here. Just like this, I could call a P sat. Okay, P I could replace with P sat. Okay, so if I do that, I'm going to have, let's see, fugacity coefficient. So now I'll call this, this is part C. So P, my pressure is equal to 0.074 bars. And then my phi, I'll just do phi2 vapor. Right? Remember, phi2 vapor is the same as phi2 liquid, is 0.9953. Okay, cool. So F2 is going to be equal to phi2 vapor times P. So my fugacity would be 0.0737 bars. So F is going to be 0.0737, 0.0737 bars. Okay, cool. So that gives me the fugacity. Then D says calculate the fugacity of methane at 250 Kelvin and 300 bars. Okay. You may assume that the molar volume of methane is insensitive to pressure, so it's incompressible, such that the pressure is insensitive to the pressure, such that at 300 Kelvin, or this should be at 300 bars, V2L is approximately equal to that at saturation. Okay, cool. So what I'm thinking of is I'm going to need the Poynting correction. Okay, so what I'm going to have is I'm going to have that the fugacity of component 2, right, is going to be equal to my fugacity of component 2 at saturation times my Poynting correction takes the form of the exponential of V over RT, P minus P sat. Okay. Remember, it's P minus P sat because this P, right, is going to be greater, so I'm at a P greater than my saturation pressure, so that's positive. All right, and so this assumes constant V. Okay, so that works for an incompressible fluid. Right, so that's V over RT. That's great, but in the problem, right, I have Z. Right, so let's get that in terms of Z. So how I'm going to get in terms of Z? Well, my equation of state for a real fluid is PV is equal to ZRT. Okay. So V over RT is going to be equal to Z over P. Okay, now the question is, well, what P do I use? Well, the P that I'm going to use, if I look back at my problem statement, right, is I'm given Z, right, of my liquid, right, because I want to calculate the molar volume of my liquid. So this is going to be the compressibility of my liquid, right, at saturation, right, at this saturation pressure. And so that would give me V over RT, and we assume that as we change pressure, that value of V over RT is essentially constant. Right? So when I write this, right, so I should say that this is VL, so this is going to be ZL over, that's my PSAT. So F2 then is going to be equal to F2 sat, which I just computed, times the exponential of ZL over PSAT times P minus PSAT. Okay, cool. So let's go ahead and compute it, right? And notice that the units of pressure will cancel. Z is dimensionless, so my exponential is dimensionless. So the units of F2 are just that of F2 sat, right? Cool. All right, so I have F2, which I what I'm calling here. And so let me update this. Let me call that F2sat. So then in terms of part D, okay, what I'm going to need to track is I need to track ZL, right? So I already have P here. I'm going to call this PSAT. And let me update that to PSAT. So then down here, I just need ZL and P. So ZL 0.0004. ZL is 0.0004. And then P, the pressure I'm trying to compute, my fugacity at is 300 bars. Okay, so F is going to be equal to Fsat times the exponential of V over RT. We replace with ZL over PSAT. So I'm putting in parentheses ZL divided by ZL divided by PSAT times P minus PSAT. Okay. I call that F2sat, F2sat, F2. Okay. All right, so my fugacity is 0.3726. So this is 0.3726, and the units are bar. All right, we're crushing it. All right, so that is D. Now E, we have a solution with composition x1 equals 0.2 that's to be stored at 250 Kelvin. It's important to avoid the formation of vapor. What is the minimum pressure required? Okay, cool. So we have a solution with a composition x1 equals 0.2 that's to be stored at 250 Kelvin. It's important to avoid the formation of vapor. What is the minimum pressure required? Okay, how I'm going to answer this, let me label it, this is E. Okay, so in terms of E, okay, I'm going to draw my good old friend phase diagram. Okay, what phase diagram am I going to draw? Well, I'm going to draw PXY. Okay, so we're asked about the pressure. Okay, so I'm going to start by drawing a PXY for an ideal system. So for an ideal system, if I plot with respect to the most volatile component, I'm going to go, this is my bubble line going from P2sat to P1sat. I've got to draw my bubble line, or my dew line. It's going to look something like that. Okay, cool. So now the idea is up here, right? This is liquid. Down here, this is vapor. And in between, I have two-phase. Okay, cool. So if I have a mixture of some given composition Z1, okay, so if I have some, so if I say my system has a composition of, Z1, in this case it's 0.2, right? It should be a little more over here, but it's all good. All right, so I know my system is somewhere on this line. Okay. Key is going to be, okay, that, this point here, so where I hit my bubble line, that's my bubble point. Okay, and on my bubble point, okay, my bubble point is unique because this is going to give me my largest possible y, right? So let me just call it y1 max. And then at my bubble point, right, I have that x1, which I read from my bubble line, is equal to z1. Right, so my bubble point, x1 is equal to z1, and that's where I get my maximum y. And my dew point down here, that's where I'm going to get my minimum x. That's where I get x1 min. And what's unique about my dew point is there I have y1 is equal to z1. Right? So cool. Now the key is okay. So I'm somewhere on this vertical line. Right? The key is if I'm at a pressure greater than my bubble point pressure, then I'm up here. I'm in my liquid. If I have a pressure less than my dew pressure, then I'm down here. I'm in my vapor. And if I'm in between, I have two-phase. Okay. So now if I look at the problem, it says I have a mixture of 0.2 mole fracs, component 1, that's to be stored at 250 Kelvin. And it's important to avoid the formation of vapor. What is the minimum pressure required? Okay. Well, the minimum pressure required, right, that's my bubble point pressure, right? Because for any pressure less than that, I'm going to be in two-phase or vapor. So if I want to remain in all liquid, I need to be above my bubble point pressure. Okay. Well, what is my bubble point pressure? Well, if I have a mixture of 0.2 mole fracs, I'm going to look for Z2. Well, Z1 is going to be equal to 0.2, and so my bubble point X1 is equal to Z1 is 0.2, and that's exactly what we're given here in row 2. So what we're given is this would correspond to the bubble point, of a mixture of 0.2 mole fracs. And so the bubble point pressure then is 6.148 bar. Okay. So in E, okay, I'm going to call it P min. All right, P min is going to be equal to P bubs for that mixture. It's going to be 6.148 bar. So if I want to keep my system as a liquid, then I need to keep it at a pressure greater than 6.148 bar. All right, now E. Calculate the volume of the tank needed to store a saturated liquid mixture of the two components with a composition X1 equals 0.2 at 250 Kelvin. All right, so now in F, okay, so basically we have that solution from E. We're going to assume it's at the bubble point, right? And so the question is, what's the volume of the tank needed, right? And I guess it's going to be, so they say report the results in cubic meters per million of moles, but let's calculate a molar volume. And then if I want to get the volume per million of moles, well, I can multiply by a million moles, and I'd get what looks like an extensive volume. All right, and I could that would be on a basis of this volume per million moles, right? That's the volume that a million moles would occupy. So I'm looking at row 2. So what I want is the molar volume. Okay, and so we kind of already did this. Okay, and so what's going to be key is my equation of state for real fluids is PV is equal to ZRT. So V is going to be equal to Z times RT over P. Okay, where I want V of my saturated liquid, so that's going to be V liquid, and so here I use Z liquid. Okay, so to get my molar volume, and now my units of molar volume, okay, are going to be dependent on the right-hand side. Okay, so what I'm going to do is I have T in Kelvin. R I can only remember in SI units, joules per mole Kelvin. So I would take my pressure, which is in bar, and convert that to pascals. Okay, and I remember that 1 bar is equal to 1 times 10 to the 5 pascals. Right, so what I remember is always the equivalence of an atmosphere. Right, 1 atmosphere is 101.325 kilopascals, or 1.01325 times 10 to the 5 pascals. Okay, well, 1 bar is approximately equal to 1 atmosphere. Right, 1 bar is 1.01325 atmospheres. All right, so 1 bar is 1 times 10 to the 5 pascals. All right, so when I do this then, okay, so this is part G. Okay, actually I already have it, right? Because it's going to be that same Z of 0. Nope, it's going to be this one, right? Because now I'm in that mixture. So now I'm going to have a ZL is equal to 0.0310. Okay, so that's ZL. Then I have P. Okay, so P in bars is 6.148. 6.148. So P in pascals is going to be P in bars times 1 e to the 5. Bam. R, well, the only R I can remember is 8.314. And then my temperature, which is in Kelvin, is going to be equal to 250. All right, and by putting everything in SI units, when I calculate my molar volume, it'll be in SI units, which is meters cubed per mole. Okay, so when I compute the V of my liquid, it's going to be Z liquid times R times T divided by P. Okay, and this is going to be in meters cubed per mole. Okay, so if I run that, I forgot a multiplication sign, so if I run that, all right, I get 1.0480, so this would be meters cubed per mole. All right, so if I wanted it per million moles, what I do is, V, my solution is going to be V1 times, I multiply by 1 e to the 6, all right, V1, what did I do? V sol is equal to, VL, right? I think this is, my issue is in MATLAB, my L's and 1's, like in this IDE, are looking exactly the same, times 1 e to the 6. So 1 million moles, right, they occupy 104.8 meters cubed. All right, so I'd report the volume as they want it is 104.8 meters cubed per million moles. So my volume equals 104.8 meters cubed per million moles. And that is problem 1. So sorry for my technical difficulties, but hopefully that explains problem 1 for you.